Yes.
Excellent. So last year we were talking about NIM and how to play NIM or solve NIM. Do you guys remember the solution? Uh, Hello. Okay, so I'll do a quick recap of last class. So NIM is a game defined on piles. So there are several piles of stones like this, and on each turn a player may take as many stones as he or she wants from a single pile, and uh, eventually the stones are going to run out. The last player to take a stone wins. So the first player who can't take a stone wins. So it turns out that for NIM, like you can just denote a game of NIM using the numbers of stones in each of the piles. And it turns out that the game is winning for the second player precisely when the exclusive OR. Uh, does everyone know what the exclusive OR is? And the exclusive OR of all the numbers is 0. Well, so in this case, the exclusive OR is uh, 1 or 3. It's 2, so it's actually winning for the first player.
Hi, so I don't know what exclusive means this like plus and
Uh,
circle sign.
Sorry, what?
So I don't know what this like plus and circle sign. What does plus and circle sign mean?
Oh, that's the exclusive OR operator. So, the exclusive OR is defined in binary. So in binary, for example, 4 would be 1. I hope everyone knows what binary is. Right?
Yes.
Yeah, binary operations,
Yes.
So exclusive OR is simply just write all the numbers in binary, and now for each digit, if there's an even number of ones, put 0, and if there's odd number of ones, put 1. So this is 0, 1, 0. This is the result.
Okay.
1, 0 in decimal is 2. So the idea is that if this exclusive OR, this game is winning for the second player precisely when this exclusive OR is 0. I already explained it in my previous lecture, so I won't be going through it again in future. Uh, I'll start with something else. So this is just a fact that you can remember for this lecture. You can take it for granted. So now the idea is that basically there's a whole class of games called impartial games. Uh, Partial games. So there's whole class of games called impartial games where the games are essentially equivalent to names. So for any game, you can write a
Voice is not coming.
Am I audible now?
Yeah.
Cool. So I was talking about impartial games. So impartial games are defined as games which are sort of equivalent for players. If you switch the players, the moves remain the same, like the moves that they can legally make. So for example, NIM is an impartial game because if you are the first player, you can take any number of stones from any piles, and if you are the second player, you have exactly the same set of moves. Like it's no different if you're the first player or the second player. This is in
So if both the
contrast to
players have
say,
same set of so if both the players have same set of moves, then it is called an impartial game.
yeah, like if it was the other player's turn, they'd also have the same set of moves. And this is in contrast to games like chess, which are partial games, because the white player only moves white pieces and the black player only moves black pieces. That would be what is called a partial game.
Oh, okay, okay.
So there's a theorem called, which is a rather important theorem called which states that every impartial game is actually equivalent to a name game in a certain sense of equivalent. So equivalent means that you can essentially match moves on a impartial game with the moves on a particular name game that it is equivalent. Or more generally, two games are said to be equivalent if you can sort of match moves in one game with moves in the other game. So some move in the NIM game corresponds to some other move in this impartial game that we have, and so on. Like so that the position always remains equivalent after the moves. And Sprague-Grundy theorem states that you can always do that. Like you can always find a NIM game equivalent to the impartial game that you have. So before I formally state the theorem and try to prove it, I will try to define a construct called a formal formal game. So so it turns out like for games you often define boards and pieces and all that, but it turns out what you really care about is the game tree. Like after what move can you get and so on. Also for NIM games, one thing you want to remember is how to add games. Like for example, if you have a NIM game or so any NIM game can be seen as a sum of different piles, where sum of games is defined as so sum of two games G1 and G2 is defined as the game where every player could either move on G1 or on G2, but like exactly one of them. This is defined as the sum of two games. So it turns out that if you remember, if you were in my last lecture, you'll remember why this construct is very important. Like this is the construct that we use to prove the NIM theorem. So this is a construct that you always want to define when you're dealing with combinatorial game theory. You want to be able to play two games at the same time. And so formal games are defined. Oh, in particular, one thing you need to note is that you're playing on two games at the same time. Then for each game, you need to remember the moves of both players. That's one particular thing I want you to remember. So this motivates our definition for a game, for a formal game, let's say. So the idea is that you can define a game to be just a pair of set of games. So a game is defined as like a pair L/R, So this corresponds to the moves of the left player or the first player, and R corresponds to the moves of the second player. Because you need to remember both of them. And here, here you have that L and R are both sets of games. These are both sets of games. So when you're defining a formal game like this, can you see why it's actually equivalent? Like any two-player game can actually be expressed as a formal game. Can you see why that is true? Like all you care about is the sequence of. So let me construct a few formal games for you. Then maybe it will be. So the most important game is obviously the trivial game where neither player has any moves. This is called the trivial game, where both sets are empty or sometimes written without writing anything. So these are both empty sets, and so the formal the game zero corresponds to game where has any, so the game is already over. Now this is not the most interesting game to analyze, so we'll define some more complicated. So by the way, impartial game in this definition, impartial games correspond precisely to the games where L equals R. L equals R, and all the games in L and R are all impartial games. You need L equals R, and every game in this set is impartial. Every game in L and every game in L equals R is impartial. In that case, you will know that the game. I hope that's clear. Like for an impartial game, both players must be able to make the same moves, and following that move, you must have an impartial game left. So now let me define some more games. In particular, let me construct all the nim games as formal games. So the simplest nim game is the nim game on one pile with exactly one stone. For that position, you can actually only get to 0. So that position is called 0/0. And this is actually called *1. 0 is also called *0, but these two are actually equivalent. So 1 is actually a different game that will come to later. But the nim games are all written by the nimbers. So by the way, this exclusive or sum in the nim game that I just showed you, this exclusive or that you compute to like evaluate the nim game, the value of this exclusive or is actually the value of the game as a nimber. So it turns out that this game is actually equivalent to the game *2. In the sense of equivalence that I will define. And let me just define what all the star numbers are. Star n is the nim game on a single pile with n stones. So you might guess what it is already. So it's defined as the *0, *1, so on until n-1, and the right side is the same. It's the same thing. Okay, yeah. Can you understand why *n corresponds to like a nim game with n stones on a single pile? like if you define it like this inductively.
Hi. So I didn't actually understand the L slash R thing. Like L is a set of games. So like, how does this make a game?
Uh, Actually, when I say game, think more of position. So when I say a formal game, I mean like a formal position in a game. So like in this setting, we don't distinguish between games and positions of games. So when I mean L and R are sets of games, they are sets of positions that this given
Characterize the game.
position can lead to. So think of this. So here you can make a move on any of the three piles and go to a different position like 4, 1, 5. That's a position you can go to from this position. So all L is the set of positions that this game can go. But as I told you, every position is essentially a formal game. Like it can be written as a formal game. So for each of these positions, we break them down into formal games as well. So from 415 you can like go to 315 or 411 or many all of these positions and so on downwards until you get the position where there's no moves playable. So the empty name game where there are no stones. That position is equivalent 0 because there you can actually make no moves in either case. So that's actually equivalent to 0. You can actually realize that the position with exactly one stone is equivalent to star 1. And then the position with exactly 2 stones is equivalent to star 2 and so on. And after that, you can actually add 2 games. So the position with 3 stones on one pile and 2 stones on the second pile. Now,
Okay. Yeah.
actually
So
to define,
suppose like player 2 makes a move, doesn't that change the set of positions? Like if it was L, then after player 2 makes a move, then doesn't it becomes L dash?
no, so L is a different set of position. Like L is also a game. So L is also equivalent to LL and say LR. Okay. So now when player 2 makes a move, it goes to the position LR or it goes to some position in LR which is say, so if you essentially playing a game normally corresponds to taking one position out of L, then the second player takes one position out of the R that is left, and then the first player again takes one position out of the L that is left, and so on. So from LLR, the second player chooses one move, and
Okay.
now
Yeah,
from
that is fine.
LRL,
Uh, I was asking like, uh, so like suppose the game is like this, person to like person to plays, and then the whole set changes. It can be like that also, right?
what do you mean the whole set changes?
Like for example, uh, first player 1 plays something, then player 2 does something, but initially player 1 had a set like S, so he could choose from let's say these positions, let's say 2 positions. After player 2 made a move,
Oh, so
then the whole
no,
set.
no. So this LR does not come from R. So this LR comes from L's move. So after L makes a move, you have a set of positions left, right?
Oh, okay.
So
So
L
this
has
is
L has a set of positions. Chooses one position out of that set. Now that position is the new position. Now right must place a move that is available in this new position that L has already chosen. And once right chooses a position among the set of positions that he is legally allowed to move to, after that left must choose a position from the new position right has moved to. Do you understand?
okay. So is it something like this, that the the whole set is like all the possible game things that are possible, and the first
Yes,
move
yes.
is like for example, if someone is playing like the first thing like changes the set to a subset.
No, it does not change the set to a subset. The positions here are themselves games. So let me illustrate it for you. So consider the nim game with exactly two stones on one side. Okay. Now this game is actually equivalent to, I'll claim, to the game consisting of the empty game and the game with mm, only the empty game twice. Okay, this is actually pretty hard to do. Wait, let me make a text box. So this is actually equivalent to so this is the game that this particular position is equivalent to.
Uh,
This
like
is the game that the position with exactly two stones is equivalent to.
like
Can you
in the
understand? So
how are there more than one slashes here? Like, shouldn't it be like a set
so
and slash a slash set? Like
so
there are
okay.
Then
So
see a set. So
this is
that is
a set with two elements, and this is a set with two elements. This is how it's traditionally notated in combinatorial game theory. The notation might be slightly confusing at first. So this big slash in the middle is actually the slash that corresponds to the outermost game.
oh
So
okay.
here you are, on the left side you have two games that the first player could move to. They could either choose both stones, in which case the new game will be the first one, where neither player can choose any stone, or he could choose exactly one stone, in which case the new game will be this one, where the second player could choose, well, choose to take the only stone that he has, which would lead to the game where neither player has any move.
Oh, so
The
okay, I
game
think
essentially ends when
okay. So is it like this that like the player one chooses, let's say, the second of its elements, and then the player two doesn't choose from
yeah.
its elements, but from the game that the player one chose.
Yeah, this becomes the new game. So once this is played, what is left is the game with one
Okay,
stone. So the second player can't just move in the game with second stones now. This game is
okay,
done for. Like
understood.
this game is finished. Yeah.
Okay.
So I hope everyone has understood like what a formal game is. Okay. So now can you see why star n denotes the, or why star n is essentially the game with n stones, n of these, where
Hi.
star n is
So
inductively defined like this.
Staren
Yeah,
was like Nimgin with n piles, was it?
no. A nim game with a single pile with n stones.
Okay.
So you have to prove that it's essentially the same thing. Like if it's inductively defined as I have written. So the right
Okay.
hand side
Yeah.
has the exact same thing as the left hand side.
Yeah. So
Is
I
it
understood
obvious?
this. Yes.
Yeah, this should be obvious now.
Yeah.
So now let me formally define the addition of two games. So I've written down what the addition of two games is. So again, the inspiration for addition comes from nim. So if you have a game with n piles and if you have a game with m piles, you can player gives two piles where the first one has n stones and the second one has n stones. This is the sum of the two piles. So the idea of this at sum game is the game where each player can choose to make a move in either of the two games. So now we have to write this down formally in our new notation that we have. So say the two games are G1 equals L1 R1 and G2 equals L2 R2. It's not very highly legible, but okay. So now we want to define the sum of the two games G1 plus G2. Okay, maybe does anyone want to define it for me? Like, do you have any guess for what this should be? Like, this will obviously be recursive in L1 and R1, and or L2 R2, and you will need the idea definition of sum recursively on the smaller games or smaller sets of games.
I mean, won't it just be like whatever this set here is, like let's say any element of L1 plus all the like for plus G2, and that's a set, and then you have the set of games
Yes.
and so on.
This will be L1 plus, where sum is essentially done on every pair, and
okay,
union L2 plus G1, and similarly on for the right. Does everyone see why this is the case from the definition of sum that we were using?
Like I have a little doubt. Like, wait. So G1 plus G2 means we can play both moves, like not simultaneously, right? Either
Yeah,
here.
you must play one move on exactly one of the two boards.
Okay.
Or one.
So like, why does this thing come here? L1 plus G2, and also what is that symbol in between?
That's a union, but it's looking like a V for some reason because my handwriting. By the way, these sets are defined as like sums of L1 plus. This is defined as the set of all sums. If you understand that. This is simply the set of all sums. Is that okay? So
Like
basically, the idea
these are games in themselves, right? So, like,
these
what
are
does
not.
it mean?
These are sets of games.
Okay, yeah.
So it's the set of set of all possible sums from L1 and G2. So do you see why this is the case?
Yes, like a little bit, I think. Wait, so okay, yeah, I think I see it now.
Yeah. So that's it. I'm not reading chat. If someone could, I mean, there's not much activity on chat anyway. So
there's nothing in the chat.
yeah, never mind. So I guess I'll move on. So once you've defined the definition So another thing you need to see that this definition is commutative and associative, which is sort of easy to see. I'll skip that. So this is essentially, and so any game plus 0 is the game itself. 0 is an additive identity. This is why it's called 0. G plus 0 equals G, and so on. And so now you can also define a minus G. How should minus G be defined so that we get that G plus minus G? Oh wait, I haven't defined equality. My bad. So actually, I don't need to define equality, or do I? Yeah, I actually should define equality. So equality essentially means equivalence. So okay, no. So this equality means like exact formal equality. To define equivalence, I'll actually need minus C. Yeah. So that is actually more convenient for me. At this point, right away, you won't actually have G plus minus G equals 0 because our definition of equality won't be strong enough. Or would it? Actually,
how was minus G defined again?
I'm asking you to define minus G. Minus G is sort of the game that is the opposite of G. Like the idea is G. If you play on a game that is G and minus G at the same time, then it's okay. So one important thing you need to know about 0 is that 0 is the only game that is second player win. Okay, not the only game, but I mean, yeah, it's the only game that's a second player. Like whoever plays second wins. So if L plays first, L loses. If R plays first, R loses. And so for equivalence to 0, you can actually have a simple definition. So a game is equivalent to 0 if and only if G is a second player win. This means that if L starts, R wins, and if R starts, L wins. This means that G is a second player win.
Like LR, if the game was LR, then isn't RL just fine or something?
Think a little deeper.
Okay.
Like on the outermost level, it should be fine. But what about on the inner levels? Like after a move, after R plays a move, it will be looking like if the moves after R are like RL and RR, then after a move on R, the game will look like RL/RR. Whereas you want it to look like RR/RL.
Right. Okay.
Sort of. So what should the recursive definition actually be? It has to be recursive in minus. Like you're close, but anyone wants to guess again, or should I just tell you the answer?
Oh, right. We'll have to change every game, right? Every game in the set.
Every game internally, yeah.
Internally, just switch every game and it's fine, I think.
Yeah, so recursively you can just define it as minus R minus L.
Yeah, okay, fine. Just same thing, right?
Yeah, it's the same thing essentially. So it turns out that this is equal to 0. So this is how you can actually define equivalence to 0. Because equivalence to 0 is the second as saying that this game is a second player win. But once you have equivalence to 0, you can actually define equivalence between, and once you have negative, like the negative of a game, then you can just define a plus b, a equals b as being the same as a minus b equals 0. So this is my definition of, this is the definition of equality for like non-zero games. This is how you define equality. A equals b is defined as a minus b equals 0. This is sort of why I wanted to define the negative of a game. So on a more like real game perspective, the idea is that two games are equivalent if playing the first game and playing the second game with players reversed is the same as saying it will be a second pair win. So the idea is so the idea of equality is that you should be able to match moves in A with moves in B. So the idea of a second player win is that for any move that a player makes in A, the other player can make a corresponding move in B, and then the game will remain at 0. So this is the key idea.
So
To define.
sorry. So we'll need to define something like where like the first person loses, right? Like
Yeah, I said that A minus B is a second person win.
no, like the game we are building every game with like 0 star 0 or whatever it's called, right?
Not necessarily. There are other games too. Like there's
Yeah.
so star games are all the impartial games, but there are partial games too that are
Yeah,
possible.
yeah, that's what I'm saying. We need to define the negative of that as well, right? Negative.
Yeah, we need to define where it will, where the first player will win and the second player will lose.
We'll need to define minus of star 0, right?
I mean, we know what. I mean, we already defined minus for all games. Like minus of a game is simply minus r minus l. That's true for all games. Like that's a global definition.
No, but okay, right, fine.
Okay, so for impartial games, the thing is that the negative of a game is the game itself because of the copycat strategy. So if you have an impartial game, then the negative of the game is the game itself because R equals L, and R and L are both impartial games. So by induction hypothesis, you may assume that minus R equals R and minus L equals L. But then R equals L, so R slash L is also L slash R. So minus C is simply G for impartial games. That's sort of the reason why impartial games work modulo 2. Like that's why you have this exclusive OR thing coming up. It is because impartial games work modulo 2.
Right, makes sense.
Do you get my point? Yes. So now here's the claim. The claim is that every impartial game is actually equivalent to star n for some n. Every impartial game is of this form.
Could you repeat the claim?
So my claim is that this one or the one that minus equals G for impartial games. Which one do you want me to repeat?
The claim that you were saying that the claim is star n will be equal to. I could not hear anything after that.
No, so star n for any impartial game, there is a n such that that impartial game is equivalent to star n. So these star n's actually constitute all impartial. Like every impartial game is equivalent to some game of this one. Every finite impartial game. We are only talking about finite games now. So in fact, even for infinite games, actually this holds. Like generalization of this, but I'm not going to talk about infinite games now. So the claim is that every finite game is equivalent to star n for some n.
So like even nim games with 2 piles or something are equivalent to one with has 1 pile.
Oh, so you don't remember the NIM lecture, like you weren't there at during the NIM lecture. So in fact, we actually proved that during the NIM. During we needed that result to prove the fact that NIM or like the NIM theorem. So if you have a game with one A piles and B piles, then that game is actually equivalent to the game with A plus B piles, where you have this exclusive OR for this plus thing. That's why this number is actually important. This is actually the single pile game, this 2 pile game is equivalent. And we actually proved that last day.
Okay.
So can't we just do it inductively or something? Like,
yes, we will be doing it inductively. So
like for right, okay, let me formalize it.
this
Like okay, the set of positions you can go to is
suppose you have let me simplify things. Suppose you have a game S/S.
yeah.
Now what?
So every game in S is equivalent to a NIM game by induction.
Correct.
Now we just want to show that any set of NIM games is equivalent to another NIM game. Like, if that's the set of positions you can go to.
Yeah, okay. So what is that?
Yeah, so we just need to build a NIM game for that, right? If that works, basically.
No. Are you planning to like do the name addition on the set?
Not
Because
exactly.
that would not be good.
Yeah, because this is the resultant, right? This is not like
Yeah,
before.
that is not the thing that you want. What is the thing that you want? Like it even gets its own name in like for Sprague-Grundy. Like that's
Yeah,
the main point of the thing.
yeah. So like I'm saying, you want a name game that ends up resulting in a bunch of like name games, kind of. Like
I know what you're saying, but can
like
you
after
formally tell me what that is? Like
yeah,
once you know S, so
yeah, okay.
suppose S contains N1, N2, and so on. Say Nk. Can you tell me what the game is? Or rather tell me which N, so what this N is, instead of like
Yeah,
what that is.
that's what I'm
So
trying to get.
what is this N as a function of N1, N2, N2?
Yeah, okay. Right. So we must be just able to get to n1, n2, and like whatever the set is, right?
You already know N1 to Nk, so you have to define N as a function of N1 to Nk.
Okay, okay. Yeah, this should be fine, I think.
By the way, Abhay, is it fine if I go till like 8:45 since I started late? Fine.
He said it's fine on the chat.
Yeah. So do you want a hint or something?
No, just give 2-3 minutes. No,
Yeah. Okay. So
I mean it's new, so it takes a moment to imagine.
yeah. I'll be back in like 2 minutes. Any progress?
Just a minute. Like we want to be able to like set up a game where like something where you can, okay, how do I say this? Like n-1 things taken at a time and you're basically able to remove them or something like that.
You're on the right path. So maybe try small cases for n. When will n be 0 or when will n be 1? Can you make guesses for those? Okay, first tell me when will n be 0?
uh when will n be 0? Like when the second player is winning, we just know that like the sum of the things.
No, I mean in as a function of n1 so on until nk.
Oh, just sum of them is non-zero, I think is fine, no?
What? What did you just say? I couldn't hear you, sorry.
uh nothing. Nothing really.
Hi, so
So
like the general game, like we are trying to prove this, right? That L/L, that this game is equivalent to some name game.
yeah, this S/S is equivalent to star M, where S is equivalent to like the games in S are equivalent to the name games on star N1, star N2, and so on. This is by induction hypothesis, and we are trying to construct N as a function of N1, N2, so on until Nk.
I mean, if we can set up such that multiple pile game also that results in this, then we can just say we can sum them, right? And
You can't sum them. What you're thinking of is not actually true. Like this set is like a set of different positions you can go to. It's not
Oh,
like
no, sorry. I
it's
don't.
not like a set you want to sum together. It's not that kind of a set, right?
No, that's not what I meant. I meant like if there is a game, like a multiple file name that
Yeah.
results in just this set of names, then
Uh, that is not true. For a multiple file games, the set of games that it will result in.
if you could control that, but then those set of files are equivalent to a name game already, so we are fine.
Oh. Yeah, no, that's not going to work.
Oh, okay.
Hi, so like I didn't completely understand. I think so S can S contain a game which is like non-impartial?
No, S is a set of partial games. Sorry, set of impartial games. I mean.
And those
So
games are also a set of impartial games. Like the whole thing is
that's the
impartial.
definition of an impartial game. That's the definition of an impartial game. An impartial game is a game where L and R are both equal to some set S, and S is a set of impartial games.
Oh.
So
So
since S is so each of the sets in S are also like sets of impartial games by definition of impartial.
okay.
And
Like
so we
shouldn't
are
this mean that okay, so shouldn't this mean that the number of games in S is like n is n, because otherwise like these games are equal, that must mean that uh, the player can choose the games that the player can choose are have same coordinately, like star n
not necessarily, not necessarily. So the same move might be accounted to two different moves.
oh okay. What do you mean like the same move can be accounted to be
So like when you are trying to prove that two games are equal, what you are really trying to prove is that the difference of the two games is zero. And we know that for impartial games, the negative of a game is simply the game itself. So what we are basically trying to prove is that uh, S slash S plus star n equals zero. So we are basically trying to play these two games at the same time. So by counter, what I mean is that when someone makes a move on like S slash S, there should be an opposing move on star n such that the game still remains zero. That's the idea of a two-player win.
Okay. I see.
So first tell me, when is n equal to zero? For what conditions on S or what conditions on n1 so on until nk? Um, Actually, maybe I should reveal the answer at this point. This is
Yeah, okay.
maybe okay. So maybe I'll tell you when it's zero. So it's zero when S does not contain zero.
Okay, yeah, makes sense.
That should have been obvious in hindsight, but I can
Yeah, yeah.
understand why it's hard to see.
Yeah, okay.
So now, when will n be one?
Uh, when will n be like the only game can be like both sides must have zero in n.
No, what if S has 0 and 2? Won't n still be 1?
What did you just say?
Suppose S has 0 and 2.
S has zero and two. Okay.
Won't n still be 1?
The resulting. No, I mean, how will it be 1 when 0 and 2?
So I claim that if S has 0 and 2, then N will actually be 1. So I claim that I can beat you as the second player. So the idea is, if you play on 0, I play on 1, and the game is over. And if you play on 2, then from 2 you get to the position, like if you play towards 2, like this new thing is 2 now, then I can just simply reduce the 2 to 1. And it's still 0.
I didn't quite follow. Can you like? Uh, I didn't quite follow.
So from this position, you can either go to 0 or 2, right? And this position,
After reach. Oh, you're saying, yeah, okay.
no, S equals 0, comma 2. So from this position, you can either go to 0 or 2. And from this position, you can only go to 0.
Yes.
That's the idea, right? So
Yeah.
suppose there are 3 possible first moves you can make, right? So what I want to prove is that this sum is a second player win. Is that okay?
Right.
Like, that's what I want to prove. Now there are 3 possible first moves you can make. The first possible first move is you choose 0 on the first game. Then I simply choose 0 on the second game. Another possible first move is you choose 0 on the second game, in which case I choose 0 on the first game, right? And the third possible move is that you choose 2 on the first game. In that case, the new game is from 2 you can actually go to 0 or 1, right? And if you choose 2, then you still have 1 here. So from 1 you can go to 0.
Okay.
But now I wish to prove that so the new position is 2 plus 1. From that position, so if you choose 2, I choose 1 here on the next move.
Yeah, okay, got it.
And there's a 1 left here. So now this is just 1 plus 1 equals 0. You understand?
Yeah.
So essentially, if you have a number greater than n here, that does not make any difference, because if you go to a number greater than n, then I'll just reduce it to n. From here, I can just go to n, and that would be n plus n equals 0, which is what I want. Like after my move,
Right.
as a second. So the numbers greater than n do not make any difference. And if you have all numbers less than n, then this can very well be n. So what this n is called the minimum excludant of s. It's called max s. This is the smallest number in the set. That is, it is the smallest natural number that is not present in the set. Oh, including 0.
Smallest whole number.
Smallest whole number, whatever.
Yeah. Okay, nice.
So is it clear why it's a minimum excludant to everyone? Okay. Like,
Actually, I understood the two things. Did we do general right now?
and the general thing is the same. So if you have like every number smaller than s, smaller than n, and
Yeah.
you do not have n, and you have some numbers possibly larger than n. If you go to a number m which is greater than n,
No, wait.
go to
We choose n, right? N is not given. We have to show that there exists an n such that this is 0, right?
yeah, I'm telling you what the n is. I'm telling you that n is the minimum excludant of s. It's the smallest number. It's the smallest whole number that is not present in s. That's what I'm telling you n is. After that, we have to show that this sum is actually 0.
Okay, yeah. So, like, okay, I'm done if the larger numbers don't matter. Can you just once repeat while, like, larger
Yeah, so
numbers don't matter?
suppose you go to m, which is larger than n.
Yeah.
On the first board. So the new game on my turn is m plus n. But now I simply
Yeah.
go from m to n on my turn. And so now the new game is n plus n, which is equal to 0. Which
Okay.
is
Yeah.
all
Okay.
we need to show.
Okay. Yeah. Understood.
Cool. So this essentially proves the Sprague-Grundy theorem. Actually, it was actually not that difficult if you think about it now.
I,
But
I think one of the confusions I had was like, what does like basically we're trying to say like star n such that star n and this is essentially resulting in a zero game, right? Or,
yeah,
and a zero game is anything a game that's second player wins, right?
that's by definition, yes.
Yeah, so that kind of between the new definitions, it kind of got confusing what we were even trying to show.
Yeah, okay. Yeah, that's how we sort of define second player. Actually, you can actually show that 0 is the only game where the second player wins, like by the formal definition of game. This actually need not be a definition, but I'm doing it for convenience.
No, like
You can actually prove that. So
what is
for
what? Sorry, what is the definition of zero even? Then I missed something that means.
yeah, 0 is defined as this.
Yeah. Even I have a doubt in like definition of zero.
Definitely,
Initially,
0
I
is
thought zero is like nobody has no move, and
yeah.
as
That is the definition of 0 is the game where both L and R are the empty sets.
yeah.
That's the
Okay.
definition
So
of 0. But the definition of equality to 0 is, I'm saying, it means second player wins. The reason for that is like the reason for defining equality in this way is that you can prove that the only game where the second player wins is 0.
so like someone will win, right? So won't this mean that there are only two games?
No, there are 4 kinds of games. The games where the left player always wins, the games where the right player always wins, the games where the first player always wins, and the games where the second player always wins. So,
Oh, so like
so for
in
games,
total, like
so that
with
idea,
this. Okay.
yeah,
So I was confused. Like with this definition of zero, won't we get like 1/4 of games are zero?
uh, no, it turns out that the 0 is the only game that is 0 in some sense.
Okay, so like
So
how can we prove that?
you can think of equality as defining equivalence classes on games. That's the best way to think about it. So you're
Yeah, that's fine. Like, won't this mean that like star one, star two, like some of these are zeros only?
no, none of star n is 0 because see, star n is not necessarily. In fact, star n is a first player win, right? It's not a second player win. It's never a second player win. In fact,
Oh, okay, yeah, okay,
it's in fact always going to be a star first player win.
okay, yeah.
Precisely because you can just reduce to 0 on the next one.
So like, isn't this definition of zero too much? Because either something is
No,
zero or
it's
first
not.
player.
It's not, Steve. You want every second player. See, second player win is a pretty. What should I say? You sort of need this to be true for like equivalences of games to behave in the way that you want. Let's just put it that way. So there's an alternate way to define equivalence that I defined in the last class, but I'm not going to go through that because this is actually a much cleaner definition. And it turns out that you need this to be true in some sense. If you want to like say some different games are equal because they behave in the same way.
Okay, so okay, now I understood why I was confusing. I was getting confused. So like 0 is equal to where second player wins. So
Yes.
second player win is equivalent to second player win.
Yeah.
But is it like first player win not equal to first player win? Is it so?
Not necessarily. So
Oh, okay.
the definition, we are defining it this way because we want addition to work out nicely. So the idea is no matter how many instances of second player wins you add, you will always get a second player win.
Okay, yeah.
But
Now
this
I
is
got
not
it.
true of first player wins.
Yeah.
This is a key point. So the idea is 0 plus 0 equals 0. This is the main point. So second player wins have this property, but first player wins don't. That's why first player wins have like a complicated additive structure, but second player wins are trivial.
Yeah, now I
So
got
this
it.
is why we want to say that there is exactly one second player win, like because second player win plus second player win equals second player win.
Yeah, it got confusing just between the definitions of stuff because a lot of it is just new.
Yeah, I understand. So now I want to talk about partial games or like games more general. So now I want to talk about one particular class of games, one particular class of partial games called uh, cold games. Cold games. Cold games sort of cold games sort of correspond to zugzwang positions. If you know what zugzwang means or play chess, I mean, if you play chess. So cold games are games where neither player sort of wants to win, like wants to play like the other player. They want the other player to go first. So 0 is a cold game because obviously it's a second player win. But there are other cold games too. Like so to illustrate the idea of a cold game, I will okay, how do I change colors in this thing? Right. I will talk about something called the red-blue hackenbush. Uh, uh, yeah, so I'll define a game called the red-blue hackenbush. So the idea is that there's this floor, and then on that thing there are some blue dashes and like blue branches, and say like there are trees on this, like in the graph sense of a tree, or in fact you don't even need to have a tree. You can have a graph in general of where the where the edges are colored red and blue, something like this, for example. It's a graph with edges colored red and blue, and some nodes of the graph lie on the floor. So the idea is if any disconnected component of the at any move, a player may decide to remove any edge of their color. So blue can remove blue edges and red can remove red edges. And for the purposes of the game, like formal games, we will assume that blue is the left player and red is the right player. So the interesting interaction is that if there's any component of the graph that's not connected to the floor, then that component gets deleted immediately. Is the definition of the game clear?
Yeah. So the graph can the graph be anything like, or is it like a tree?
Yeah, the graph
Like,
can be literally anything, like any finite. Like for the time being, we only talk about finite games. So it can be any finite graph. And
Okay.
I think
So
some of
any
the
graph.
nodes of the
Okay.
some
Okay.
of the
Understood.
nodes of the graphs are said to lie on the floor.
Okay.
Okay, and you can have multiple nodes on the floor, and say different parts on the floor can be disconnected. So this could be a very valid hack and bush game. So the idea is the last player to move wins, like as usual. The player who can't move loses, similar to NIM. So the thing is, we want to compute the formal games for these and eventually figure out who's winning which game. And since like sort of different, oops, sorry. Yeah, since different games are like different nodes on the floor correspond to like separate games, the addition of games here also makes sense. So the framework that we have makes a lot of sense. So now I want to talk about some simple hack and bush games. So by the way, the negation of hack and bush games is very interesting. It's the same game but with colors reversed. Can you see why that is true?
What
I
does
guess so.
what does negation mean?
Like minus C for G. Like the game which when added to the given game results in 0.
I mean, just place these two together and just play
Yeah.
and make a
It's just
symmetric
use
move.
the copycat strategy.
Yeah,
Exactly.
yeah.
Okay. Yeah.
So this is an example of a partial game since blue can only remove blue edges and red can only remove red edges. So the game dynamic is different for different players. So let me start by giving you some simple examples of hack and bush games. So the simplest game is 1. Like there's only one edge starting from the floor. This game is called 1, like when it's blue and -1 when it's red. So this is why we use the start numbers for the NIM games. So the start numbers add differently. So the start numbers add according to the rules of NIM, but these numbers act very much like real numbers or integers. For the time being, integers. So
Isn't there something like you can easily just create halves and all?
yeah, you can easily create like any. I actually wanted to show how to create all surreal numbers. So we'll start simple. We'll start with the integers. So once you have 1, you can easily make n copies of 1, and you will have, well, n. Or there's another way to create n, like create a tree with n edges. So this is equal to n. So the numbers are sort of equal to the number of free moves you have. So in this game 3, blue can make 3 moves and still be in the 0 position. It's sort of the number of free moves that you have. And the position with exactly 1 red node is -1 because, well, it's the negative of 1. And we sort of treat, oh wait, is that how we want to do? Actually, scratch that. Actually, we are taking red nodes to be the right ones, right? So
Blue was right. Blue, yeah, red was right.
red was right. Right?
Wait, we no longer have the equivalence, right? Otherwise, it just becomes like 1 is equal to 2. Like
What
if there are
equivalence?
the like second player win equivalence, like 0 is equal
Yeah,
to
no,
2.
you still have the second player win equivalence. Why not?
So like if there are 2 red edges and 1 red edge, then these are equal, I think.
Why is it equal? Like it's a first player win in both cases. Like it's
No,
not a first player. It's a red
wait.
player win in both cases. So it's not equal, right?
It's like suppose red is equal to second, so it is a second player win, right?
No, but what if red equals red and blue are not canonically first or second players? They are red and blue players. So so one thing you need to understand about these games is that these games don't encode turn information. It's just the position, not the turn. So the turn could either belong to the left player or to the right player. So that's why I'm talking about. So this blue game is a left player win, and this red game is a right player win. That's how we are going to talk about it. A second player win is a game where if it was left's turn, then it would be right's win, and if it was right's turn, it would be left's win. That's the definition of a second player win. And the definition of a first player win is that if it was left's turn, it would be left's win, and if it was right's turn, it would be right's win. And a game is left player winning if left wins in both cases, and right player winning if right wins in both cases. Do you understand it now?
So like the moves aren't alternate.
No, the moves are alternate once you start playing the game, but no turn is assigned initially. Like for the formal games, turns aren't assigned. Like there's no turn information associated with this game. So you could like say, okay, so if left starts, then this would be a win for left. You could say that, but you can't say this. Okay, it does not make sense to say like the game is supposed to proceed. So if left plays the first move, then right will have to play a move on right and so on. Once you assign a turn, the turns are defined. But before you assign a turn, turns are not defined.
Okay, got it.
So you want to consider both turns. Oh, I explained the reason for this as well. The reason you want to consider both turns is because you want to add games. So when you're adding games, like the game, like a player could pass on this game and play on some other game. So the turn will switch on this game. So either player could make the first move on this particular game, since there are other games where other players could move on. So you don't want to encode turn information. You just need to encode the position. Do you understand why we have this particular definition now?
Like I
With
understand
respect
the
to addition.
definition.
No. Do you understand why we have this definition? Like why we don't encode turns? Like to have the addition. Like if we encoded turn, adding games would be impossible. So if we encoded turns, if we say only cared about the game where it left moves first, then we sort of lose a lot of information about what happens if right were to move on this move. We sort of forget about that, and that's a bad thing when you want to add games.
Okay.
When you are adding two games, you want to remember how the game would proceed were right to move on this thing. So you can sort of see how the natural numbers form like 1, 2, 3. Like if you define the thing with one edge to be 1, this would be 3, because this is actually equivalent to, this is equal to 1 plus 1 plus 1. It turns out that these two games are equal. That's why I am saying this is 3. This is the simple game summation of 3 ones, and this is the game with like one branch with 3 nodes. Turns out that these two games are equal, which is pretty obvious. Like first move here corresponds to this, and then this, and then this. There's only like one sequence you can follow. So let me tell you what the formal games are. Or you could probably construct them yourselves. So okay. So for blue, we were actually saying it's. Wait, what was my convention? I forgot. Yeah, no, I want. Yeah, no. It's actually fine. We want the blue games to be positive and the red games to be negative. It's just a convention that we assume. Is that all right? So you can see why 1 plus 1 plus 1 equals like this game, and why it makes sense to define this as 3. So you can also see what the definition of 1 is. 1 is simply 0 comma, where 0 is as before, 0 slash the null set. Does this make sense to you? 1 is 0 slash null set. 2 is,
Yeah.
or in general, plus n is defined as n minus 1 slash null set. This definition should also make sense to you at this point. Like for this big tree, you are only going to chop that topmost branch off because the other moves are worse because you have less moves left. So the other moves sort of don't matter. So you can only remember n minus 1.
Yeah. So like, shouldn't it? Why other moves don't matter? I don't understand that. Like, I thought it should be 0, 1, 2 till n minus 1
Like,
slash.
okay, so my claim is that 0, 1, 2, so on until n minus 1. This slash null set is actually equivalent to n minus 1 slash null set. I claim that these two games are the same thing.
Yeah, I mean, just it's obvious, it's direct, no?
Yeah, like it's obvious because you don't want to make suboptimal moves in a cold game. So the idea is the left player already owns all of these branches, so he can make n moves in any order that he wants, right? So okay, so I'm
Okay, I
telling
got
you
it.
what the difference of this game corresponds to. This difference corresponds to this game. The game with n separate red bars and one big blue tree with n of depth n. And you can see why that is equivalent. Red plays one move, blue
This is just
chops off the topmost branch, and so on. So
this is just
the
0,
idea
right?
is in this game, blue will never chop a branch that is not the topmost branch. That's a bad idea.
This is just 0, right? When
Yeah,
you
this
have
is 0. Like that's what we need to prove that the difference of these two games is 0, or that
oh,
these two
right.
games are equivalent.
Yeah, that's
So that's the
right.
idea. Suboptimal moves never matter. Like you can always forget about suboptimal moves because the player is never going to make a suboptimal move. Like especially in a core game where, okay, so here's the idea. You can actually impose an ordering on games where one game is strictly better than another one.
Okay, yeah, I got it.
So no, I want to talk about that ordering now. This is an important point. So you can actually impose an ordering on games where
Mm. Yeah,
one game
like
is strictly better than another.
we
If
can do it like this. I think like make one blue edge as two blue edges. Then not two. I mean, if making one edge like several same colored edges, then I think this is less than that. Or maybe.
I
what do
mean,
you mean?
you're just assigning values already, right? So it's fine, no?
Yeah, but I want to talk about like relative optimality. Like I want to compare games.
No, I mean, if the value is less, then you can just say it's less. I don't
Hmm,
know.
okay, for these numbers, yes, but the idea is how to think about these in terms of games.
I mean, if just play them together, and if blue player, bl- if yeah, blue winning, then must be positive, and if red winning, then negative.
Yeah. That's the exact idea. So you define comparison with respect to 0. So 0 is smaller than a game if the game blue always wins that game. This
Yeah.
means it's a blue win and blue win and 0 being greater than the game means it's a red win. So negative games are red wins, positive games are blue wins.
Yeah, so just like if you want to compare A and B, just A plus minus B is fine, no?
Yeah, you just play a minus b. So to compare a and b, you play a minus b and compare it to 0. And
Yeah.
comparison to 0 is defined as, and equality is defined as previously. It's a second player win. And there's another thing, it could be a first player win. So suppose a game is a first player win, it's said to be fuzzy. So first player wins are actually complicated games. Like when you're adding multiple first player wins and so on, it makes like analyzing them very complicated. So I don't want to talk about first player wins now. So games which are sort of first player wins are games where you want to move first, right? So those positions are called hot positions. And hot positions are complicated because you don't know which position to move on first.
Okay.
But
Hi. Actually, I didn't uh, exactly understand this ordering thing. So, like, we say 0 is greater than red winning and 0 is less than blue winning. So, like, isn't 0 itself okay? Isn't 0 0 will all itself be either red winning or blue winning, right? Okay, 0 is second player win. So, like, why do we define this way?
sorry, I lost internet. Uh, I'll just quickly go through the rest of like. I'll quickly explain what ordering is. Maybe I'll talk about surreal numbers some other day. I'll just cover the key parts of how to construct real numbers and all that. So the idea of an ordering is that some games are strictly better than some other games for one particular player. Hi, am I audible? Hello.
Yeah, you are
Yeah,
audible.
you're
Yeah.
audible.
And I think okay. I think screen sharing stopped and I disconnected. So yeah. So the idea is a game is strictly better if it's strictly better for blue. So the larger the game is, the better it is for blue. So think about it this way. So consider these blue towers, right? The longer the tower is, the better it is for blue. Like strictly better. Like blue does not care what. Hmm. So the main point is that this idea remains preserved under addition. So if position A is strictly better than position B for blue, A is strictly better than position B, then the idea is that any position A plus X is guaranteed to be strictly better than position B plus X for B. This is the main point. This idea of being a better position remains preserved. This is because when you consider like the difference of these two positions, X cancels out, like that's obvious, but you can see why in a game theoretic sense this is true, because compared to A, B, A is always better. Like you can always emulate the moves of B and then do some more, like still have more moves left. And when you were to play on X, you can just play on X as usual. So this is why this idea of being a strictly better position matter. So this idea of being strictly greater gives us all these things, and we want to. So the reason why I defined this relation is because I want to talk about a particular class of games called cold games, which I already told you. Yeah, I've already written that down. So a cold game is there's an easy way to define cold games now. So a cold game is a game where L is less than R. Like every position in L is strictly less than every position in R. This is the definition of a cold game.
Strictly
And
less than every position in R, you said.
Yeah, every position in R is greater than every position in L. Like if you pick small l in L and small r in R, then L is less than R. And L and R are both cold games. So it turns out that less than only makes sense for cold games. For other games, it's a bit more complicated.
Because like first player win things appear and all.
Yeah, you can't sort of compare games for like star n, because star n does not have the same kind of addition. So it does not make sense to compare star m and star n, because if you add star n to both of these values, then star m plus star n is actually winning, but this is losing. But whereas if you add star m, then this one will be winning and this one will be losing. So it's sort of different for different situations. But for cold games, like it's going to be better no matter what the situation is. That's the idea.
So we can add, subtract, and all. Can we multiply as well? Like multiply. How do we multiply to arbitrary games?
Okay, so I don't want to define multiplication of games right now because it does not have a good game theoretic interpretation. Like you can define multiplication of games formally, but it's hard to give you a game theoretic interpretation of that right now. Okay. Yeah, you can actually look it up yourself on like the page on surreal numbers, or I've given you the references on the handout. Like if you want to learn more about combinatorial game theory, you should read Winning Ways for Your Mathematical Plays. Like it's the holy book of combinatorial game theory.
Okay.
And it's the same as the old handout that I shared last class. I think I can share it again this class if you want. You can get it after class. So I just want to cover some final things. So I'll tell you how to construct every real number. Okay, I'll tell you how to construct every dyadic fraction in hackenbush. It turns out that in the finite case of hackenbush, you can't actually construct all real numbers. You'll need infinite hackenbush for that. Like that should be obvious by like count, also by cardinality argument. So there are only countably many finite hackenbush games, but uncountably many real numbers. So that should be intuitively obvious why you can't make all of them. But you can make all dyadic fractions. So I'll tell you how to make 1 by n. So this particular position is equal to half. Can you see why that is true? Okay, so you have to prove that. So to prove that this particular position is half, you need to prove that this position is equal to 0.
Yes.
Is that obvious?
Yeah. I mean, by definition of 0.
Yeah, sure. So this is how you construct half. Uh, construct. Uh, Now tell me what this position is. Yeah, tell me what this position is equal to. There are like two red edges. Like should actually have made it this way, but whatever. Any guesses as to what this position is equal to? Or actually, this might be a bit complicated. Let's maybe consider this position instead. What is this position equal to? Yeah, sure. I'll start wrapping up. I just wanted to demonstrate the dyadic fractions.
I mean, it's not obvious directly. Like you'll have to kinda right now just try stuff and guess. I guess. The, I,
Yeah. Also, like the half case is also we have to check, right?
Yeah,
Suppose the first is red. Suppose the first is blue, and so on. So like.
yeah, you can actually compute it on your inside your head. Like this is not particularly difficult.
yeah, but then first in the next part you have to guess, and then we have to compute the games to
Yeah.
confirm. That's
Without
how
guessing, like, is there a way without guessing?
So, how would you expect a half game to look like? Or how do you expect a 1/4 game to look like? Say, if you are trying to construct a 1/4 game.
Like a thing, like when we do 4 copies and subtract the red edge, then it is
I
like
mean, that's a formal definition, but like in a game theoretic sense, like suppose you forget about addition and all that. Addition is like an algebraic operation. Like it's not very game theoretic. So the idea is, if you are blue, you should sort of have like you should sort of be immediately winning because it's a positive position.
ah
But if you're red, yeah, you should not be like. It's sort of hard to explain, but okay. So
like you should
so
like
this is what you will expect a half game to look like: 0/1. This is the best way to explain it. If blue plays, it goes to 0. If red plays, it goes to 1. That's what you would expect a half game to look like. So it's sort of between 0 and 1. So this is the idea of surreal numbers. So for any cold game, the actual value of the game L/R actually lies between L and R. Can you sort of intuit that, or you can sort of intuit that later? So the idea is that for a cold game, the value of L/R will lie strictly between all values of L and all values of R. That's the key idea. So to construct half, you go for 0/1. To construct 1/4, you have to go for 0/half. So if blue plays, it goes to 0. But if red plays, red will take the topmost thing, obviously, because the other thing is an option that he has but blue does not have. So if red plays red, it will go to half. So this position is actually equal to 1/4 without even doing any calculations. You can try to prove that it's equal to 1/4 on your, like, in your spare time. But
So is the idea like surreal numbers, what you're saying, that we are able to generate games and assign values, of course. So there's some game like infinitesimal, so that you can attach in infinitely many of that game, like arbitrarily many, and
so
you're
you can't
still not
attach
able to make make a negative game or something that of that form.
you can't, like, for infinitesimal games, it's sort of hard to define, like, do it by addition. Like, you can sort of look at it. So I'll give you an example of an infinitesimal game. So oops, sorry, wrong pen. An infinitesimal game would be 0/1/2, 1/4, so on. This is the simplest example of an infinitesimal game.
Okay.
So you can see that since there's no smallest number in right, but this has to be, the value of this thing has to be strictly greater than 0, but strictly smaller than 1/2 to the power k for any k. So you can see that this is an infinitesimal number.
Right.
So this is the simplest example of an infinitesimal number. So to actually deal with those, you have to sort of define multiplication and all that. So right now I don't want to define multiplication, but you can look it up on your own. Like, the more complicated operations you go to, the less game theoretic sense it makes, and the more you have to wrap your head around it. And also, the more complicated the definitions of the operations get. So, and can you tell me what the reciprocal of this would be, just by guessing?
A reciprocal.
Yes.
Okay, wow.
Just guess. It will be
I
an
can't-
infinity. It will be an infinite number. That's like,
Oh,
I can give.
you mean of the 0/1/2 1/4 game? You mean the reciprocal of what game?
Of this infinitesimal game.
Right. Okay. 0, 1, 2, 4, and so on. Sorry, infinity 1 to 4.
Yeah, that's the left side. Okay, so on the left side, you are guessing 1, 2, 4, so on. Or 0, 1. It does not matter. Like, the small games do not matter. Like, you can cut this sequence off at any point. It will be the same game. Like, because the suboptimal games don't matter. But yeah, in fact, you can just have all natural numbers. It does not matter because, well, it's sort of the supremum of all natural numbers on the left hand side. And what will the right hand side be? Like in the simplest case.
I have no idea how I even want to define a reciprocal right now.
Okay, so the right hand side will be the null set.
Okay, wow. Yeah, I don't even know what I want to define it as, like a reciprocal.
I mean, if you put any finite number, then it will be less than some element of the LHS.
So this is the sort of the simplest infinite number omega. It's not the smallest infinite number omega. There are numbers like omega over 2 or all that, which are way smaller. But this is the simplest infinite number omega. So what I mean by simplest is that the first number that occurs in, like, the sequential construction. So when you're constructing all the surreal numbers, you can actually do that by transfinite induction. Do you know what ordinals are? You are supposed to have read that up before the class.
Yeah.
You should know what ordinals are. So
yeah,
at
but,
the
I know like the basic idea, not like full.
so the main point, the thing is, the thing that you do with ordinals is transfinite induction. That's the only thing you need to know about ordinals. That's the entire point of ordinals, to do a transfinite induction. So you can actually define all the surreal numbers by transfinite induction. So you start with the surreal number that is empty. This is 0. This is the surreal number you have in the 0th step. Or actually, in some cases, you instead of defining surreal numbers, you want to define some set of surreal numbers that you have. So at the 0th step, actually, that I actually prefer that construction. So at the 0th step, the set of surreal numbers that you have is the null set, right? At the first step, you get the number 0, which has null set for both of its arguments. At the second step, you get 1 and -1, which has like 0/null set and null set /0 for its arguments. So the first is 1, the second is -1. So the idea is the null set sort of represents the supremum and infimum of all surreal numbers at the same time. Like when you are like thinking of L minus R, like this is sort of trivially true, like because R has no element, so you only care about the L side of this thing, and L has no element, so you only care about the R side of this thing. So 1 and -1 happen in the next step. After that, you sort of get half, minus half, 2 and -2, and so on. In this way, at the omega, like in all the natural, before the omega step, you get all the integers and all dyadic fractions like k over 2 to the n, all fractions of this form. And once you have that, at the omega step, you can actually get all, I think you can get all real numbers. So this is sort of the first position where the transfinite part comes in. So at the omega step, you have not only have all real numbers, you also have like epsilon and omega, and all their, in fact, all their like epsilon over 2 omega. Oh wait, actually you get those in later steps, but you have epsilon and omega and minus epsilon and minus omega at this step, and you continue this way. So one fun fact is that at the alpha step, you get a game that also corresponds to the same ordinal number alpha. Like it has the same properties as the ordinal number alpha in terms of being greater or lesser. Or so it turns out that all ordinal numbers are created internally in the definition of games. Oh, in fact, I can give you a simple definition of what an ordinal number is. It's simply, those are the numbers that in the simplest form occur with a null set on the right hand side. So if you want to learn more about surreal numbers, you can like look up the Wikipedia page or read Winning Ways for Your Mathematical Case. It's 9 o'clock now, so I'd like to end now. Is that fine?
Yeah, thanks.
Yeah.
So bye, I guess.